This conference will now be recorded.
All right, this is section 2.2. We did not get the second piece of this finished in class, and since our test is going to be next Thursday, I did not want to have to teach through this 2 days before your exam. So this is kind of where we left off. We had talked about how to graph the derivative of the function based on some key information that we saw in the actual function. Mainly, we were looking for what were the slopes of the tangent lines, because remember, those become our y values of our ordered pairs when we graph the derivative. So there were some examples there. We did all of those in class. I might do another video if I have time this weekend of maybe a third or fourth graph just to get you guys some more options of something to watch. But we want to talk about what happens after this point. So notation. Other notation for the derivative of f of x can include, we know f prime of x, sometimes we'll call that y prime, dy dx, that means the derivative with respect to x of the function y. Df dx is also the derivative with respect to x, is kind of how we read that, of the function f. Sometimes it's written this way, so that's a little bit clearer that you can see that you're reading this is the derivative with respect to a specific variable x of a function, or depending on, and this a capital D also means the same thing, and sometimes they'll put the with respect there. So the capital D and the ddx are called differentiation operators, because they indicate that the operation of differentiation, which is the process of calculating a derivative in a specific way. Now, this will matter when we get to implicit derivatives later on, because we will care what the respect of the variable is that we're doing. So a function f is differentiable at a point A if f prime of A exists. It is differentiable on an open interval AB, or you could say A to infinity, negative infinity to A, or negative infinity to infinity. Those are all open intervals. If it is differentiable at every number in the interval. So you can't say you're differentiable on negative infinity to infinity unless the derivative exists everywhere throughout the whole function. There is a theorem. It says that if you know your function is differentiable at A, then it has to also be continuous at A, because if the derivative exists, that means the point exists, and it means that we're also approaching it from both sides of the limit. So the only thing about that is you have to be careful. Just because you're differentiable at A, that definitely proves that you're continuous. If you're continuous at A, it doesn't necessarily mean you are differentiable. There's a couple issues with that, and we're going to look at them next. The absolute value function is a prime example where there's a point where it technically can be drawn without lifting our pencil, but it's not differentiable there. So there are three issues that can cause a function to not have a derivative at a point A. A corner, which is sometimes called a kink or a cusp, just depending on what book you look at. This is when a graph is changing directions abruptly. Notice this point right here. The left and right limits when computing the derivative will be different. And also the issue here is if you zoom in, anytime you draw a tangent line to something that has a derivative, you're going to notice that you get almost linear. Like when you zoom in, that's called like locally linear. You would see that it straightens out and the curve almost flattens like a line. If you zoom into this, it's just going to be a sharp point. A discontinuity can be another place where you don't have a derivative. Remember, that could be a hole or a vertical asymptote or a gap in your graph. If a function is not continuous at the point, then it does not have a derivative there. So that automatically means that it would not be differentiable at that point. If you have a vertical tangent line at a point, the slope of the tangent line becomes so steep as x approaches A, and the slope of vertical lines are undefined. So therefore, that is a problem, because the derivative, remember, represents the slope of the tangent line at that point. So these are just pictures of those situations. And then higher derivatives. So the thing about derivatives are that we don't want to just take one derivative. We're going to learn some applications of derivative in the next couple units, And we want to realize that taking more than one derivative actually gives us information that is useful for curve sketching or for talking about velocity and acceleration. So these are what we call higher order derivatives. It's when you take a derivative of a derivative or a derivative of a derivative of a derivative. Since the derivative of a function is also a function, it may have a derivative as well. And we would denote that as f prime and then prime, which we would just call f double prime. And that's called the second derivative of f. Another notation, this member was taking the derivative with respect to x, so taking derivative of. This says dy dx, that means the first derivative of y, obviously with respect to x. And notice this squares both the d and the dx, because remember that's the derivative operator. This means we're taking the second derivative or two derivatives of the original function y. So my last example here is that we have this function, f of x equals 2x cubed plus x, and we want to find f double prime, and we want to find then f triple prime, or, derivative with respect to x of y 3 times. So this will be a little lengthy because we only have the limit definition to work with right now. And again, the limit definition is so important. Even though you get to use shortcut methods in the next unit, understanding how limits work is useful for all of the calculuses. So, make sure you get this, make sure you understand how this works. So we're going to take f prime of x, which means we're going to just be doing the first derivative, so the limit, and now we're going to call this member, and it's still h approaches 0, but instead of using a in our formula, we're going to have x. So it looks very similar to what we were doing, but instead of a's, we're calling it x. If you took Math 136, we called, remember that, the difference quotient, that specific formula. So the limit as h approaches 0, so this is going to be my f prime of x, and this is, we have to plug in x plus h for all of the x's in that function. So 2x plus h cubed plus x plus h, that's my first evaluation, minus, now we're going to plug in x, which means we just write the function. But you do have to have that minus sign, all over h. I'm going to come over here to the side just because I don't want to use all my room. And I'm going to write x plus h 3 times for cubing. And I'm going to show you that this comes out to a pattern every single time. So hopefully you'll get familiar with the pattern. You want to distribute out 2 of the pair first. So that would give me an x squared, an xh, and another xh, which would be 2xh plus an h squared. We recognize that guy from some of the ones we were doing a minute ago. And then if you times that by another x plus h, you get an x cubed plus a 2x squared h plus an xh squared plus an x squared h plus a 2xh squared plus an h cubed. In other words, the pattern is the first thing gets cubed, you get 3 x squared h's, you also get 3 xh squareds, and you get 3, h cubed. I was on a 3 kick. There we go. We don't want to erase all ink. So this is just h cubed. Okay, so I'm going to substitute that in. So this would now be limit as h approaches 0 of 2 times x cubed plus 3x squared h plus 3xh squared plus h cubed. Don't forget we still have this plus x after our parentheses is closed, and plus h. I kind of already distributed that positive 1 there. And then we have our minus 2x cubed and minus x. I'm going to go ahead and distribute that negative. Okay, so let's work on this inside here. We need to distribute that 2. So this is going to be 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed plus x plus h minus 2x cubed minus x, all over h. You're going to notice a theme. Some things are going to cancel out. The 2x cubes are opposites, and so is the negative x and the positive x. Everything else is an h in it and is different, not like terms to each other. So we're just going to bring those over. And I'm going to reduce an h out of everything before I evaluate, obviously. So this is going to be 6xh plus, or sorry, that h is gone. I got ahead of myself. It's going to be 6x for the first one because the h will cancel, a 6x squared. And then this will be 6xh. And then this will be 2h squared, and then a plus 1. Now, when you go to evaluate that, remember this is going to give me my derivative. If I put in zeros for all those h's, I just get 6x squared plus 1. So I needed that. I haven't even answered the question yet. This is just the first derivative. And that's because it was an x cubed. That makes it a more complicated limit process. Now, the good thing is we get to do the second derivative now, and we're going to see that this one goes a little bit quicker because it's only going to be squared now when we work with it. So we're going to take f double prime of x is the limit as h approaches 0 of the 6 times x plus h squared plus 1 minus 6x squared plus 1 all over h. Work this out. This guy is x squared plus 2xh plus h squared. Remember, that's what you get when you square x plus h. So if I distribute that 6, that's going to be 6x squared plus 12xh plus 6h squared plus 1. Distribute my minus sign, minus 6x squared minus 1 all over h. So we get that the 6x squareds cancel, and so do the 1 and the negative 1. This is the limit as h approaches 0 of 12xh plus 6h squared all over h. And if we cancel out the common h's, we will then be allowed to evaluate the limit as h approaches 0. So this is just going to be 12x. So f double prime of x is 12x. So we just need to do this one more time to get the triple prime. Now I'm going to actually write triple prime. If you want, you can write this notation. Doesn't really matter to me. For this situation, I'm going to be doing the third derivative. So this is the limit as h approaches 0. We'll separate this out. And then we're just using 12x as our function because that was the second derivative, so we build our third derivative off of that. So it's 12 times x plus h minus 12x, not much going on, all over h. So that's the limit as h approaches 0 of 12x plus 12h minus 12x all over h. So this is just going to be 12h over h, which means that we don't have an x anymore or an h anymore to plug into. Now remember, we learned a rule that said if your limit as you're approaching something is of a constant, the answer is just the constant. So the third derivative of this function is 12. And that is the end of this section of notes. All right, so I will see everyone in class on Tuesday, and we'll be reviewing for your first exam.